Hey guys, welcome to Cougar Chem Tutoring. I'm Austin and I'll be running through part 1 of problem set 4, the mole. And then we'll be running through problems 1 through 3 here. Alright, so what is the mole? The actual definition of this is the number of carbon atoms present in 12 grams of carbon 12. Okay, so that's the literal definition of it. This was discovered by a man named Avogadro. And by default, we actually call this number, which I'll show you here in a second, Avogadro's number. So 1 mole, okay, is what we call, it's short for this number, 6.022 times 10 to the 23. Okay, oops, that's a 10. And that could be anything. In this case, we're talking about atoms, but it's really just a number. So like here, we're going to talk about dozen. Dozen just means 12, right? You don't think, oh, it's specific to eggs, so just a dozen eggs. No, you think you can use a dozen in a variety of contexts, whether that's eggs, baseballs, phones, whatever it may be. And so here, this is just a number. This could be a mole of, baseballs, of a mole of couches, a mole of shoes, whatever that may be. And it's just a number. But a lot of times we use this 1 mole in place of this number to shorten or abbreviate the numbers that we have to use, because the numbers that we have to use are generally very, very large. And so if we can just say 1 mole and that's in place of this, it's a lot shorter and it's a lot easier. So why not use dozen in the place of the mole? Well, that kind of defeats the purpose of using the mole in the first place, because if we use a dozen, if we were to use dozen in place of moles, then we'd have to divide 6.022 times 10 to the 23 by 12, and that would get us 5.02 times 10 to the 22. This is not any significant number that you need to know, although you do need to memorize this number. But if we did do that, we would say there's, okay, this many dozens of atoms. But that doesn't really help us. That doesn't condense down the number for us. And so we use the mole to be able to abbreviate that and use them in more manageable numbers, okay? So that's the mole. Now, number 2, if you had 10 moles of M&Ms, okay, so 10 times this number, how big would the box need to be to hold all of them? Okay, and then the volume, they give us the volume of an M&M, and they want this in kilometers cubed. Okay, cool. So here's the measured value that they give us, okay, starting with our dimensional analysis. I'm going to write a couple conversions over here. We know that 1 M&M is equal to 2.2 centimeters cubed. All right, and what else do we know? As far as we know, that's about all we know right now. And so this is the only conversion that I have. So I'm going to start with this. I'm going to say, okay, I know I have 10 moles of M&Ms. Well, how many M&Ms is that? Because I only have a conversion of 1 M&M to 2.2. I don't have moles of M&Ms and then, it converted into some volume. So I have to turn this into the actual number of M&Ms that this is equal to. And so I have to say, okay, I know that that 1 mole of M&Ms is equal to 6.022 times 10 to the 23 M&Ms. Okay, now if I were to stop here, okay, I would multiply 10 by that number, and that would give me the number of M&Ms that I have. But that's not what I'm looking for, right? I'm actually looking for the volume that this takes up. And I know that 1 M&M takes up that much space. So I'm going to say 1 M&M is equal to 2.2 centimeters cubed. Now, if I finish this math just as is, I would get an answer that's in centimeters cubed of the volume that I need. So I'm almost there, actually. I have a volume. It's just in the wrong unit. And so what we're going to do is we're going to convert from centimeters cubed to kilometers cubed. Now, there's not really a one way to do this. And really, you can look this up on the internet and do that, but it's not going to be helpful because you're not going to be able to do that on your exam. So let me show you a pretty straightforward way on how to do this. So what we do is, it's even though we can't really readily tell how many kilometers cubed is equal to centimeters cubed, we do know, or at least hopefully there are 100 centimeters in a meter. Okay, you know that off the top of your head, right? Now, in order to cancel out the centimeters cubed with this centimeters, we can just cube both sides of the fraction. If you don't know, if I have like x over y and have this parentheses and I cube the whole thing, that's actually equal to x cubed over y cubed. And so that's essentially what we're doing here mathematically. So now my centimeters cubed will cancel and my centimeters cubed will cancel here. But this cubed, remember, this cubed actually distributes to both the unit and the number. So here we're actually going to 100 cubed centimeters cubed. That's what this number is down here, okay? So don't forget to distribute that cubed in. And then here we would get 1 cubed centimeters cubed, which is just really 1 meter cubed. So, or 1 meter cubed and then 1 cubed. And so we'll just say it's 1 cubed. And then I have to be able to turn that from meters cubed into kilometers cubed. And so again, same logic, 1 kilometer is equal to 1,000 meters. Okay, and then cube it again so that these these meters cubed will cancel. Now, if you do that math right, okay, remember that the 1,000 down here is actually 1,000 cubed. So here we got 100 cubed, and then 1,000 cubed. If you do the math right, you should get somewhere around 1.3 times 10 to the 10th, and that would be what? Kilometers cubed, and that's the volume that we'd need. Okay. Now remember, I have switched up these numbers from the actual problem that you have. So even if you get a similar answer to what I have here, that I would not put this on your sheet. Okay. This is just for demonstration purposes. Part B says, assuming the box from part A is a cube with sides of equal length, is the side of the box closest to the radius of the sun, the radius of the Earth, the flyover distance of San Francisco to DC, or the length of Texas. Okay. And what you need to really know here is know that the volume of a cube is equal to L cubed, L being the length of this the sides of the cube. And so in order to get just L, you just cube root it, right? And so we take the number that we have, so that was 1.3 times 10 to the 10th kilometers cubed. That'll bring my my kilometers down to kilometers, and then I take the 1.3, the cube root of 1.3 times 10 to the 10th, and that'll be in kilometers. And if you do that math right, you get around 2,366 kilometers, which is closest to the difference of San Francisco to DC. Okay. All right. Now on to number 3. Okay, calculate the molar masses of the following bodily chemicals. Okay, molar, meaning how many grams does it take to get 1 mole of this stuff? And in order to do that, all you have to do is add up each component of the molecule and the elements that compose it, and add up the total molar masses from each individual element. So what we do is, knowing that there are 19 carbons, I know, okay, 19, and then I'll say 19 times the molar mass of carbon. That'll give me the molar masses of all the carbons that are in there. Okay, so that'll be 12.011 grams per mole. That is the unit of molar mass, okay, grams per mole. And notice that I had mentioned this in a previous video when we were using atomic mass units instead, and had mentioned that we'll mostly be using this, and that's where this is going to be coming into play. All right, so that's just the component of carbon, okay, and then I do the same with hydrogen. I know that there's 28 hydrogens, and I multiply that by the total, by the molar mass of hydrogen, so I know that how much of the molar mass is from hydrogen in testosterone. Okay, and then do the same thing with oxygen. So 2 times, and then you get remember, you get these values from the periodic table. Okay, so this is where I'm looking for these, and then grams per mole as well. Okay, now if you add these up correctly, you should get about 288 grams per mole. Now what does that mean? That means it takes 288 grams to get 1 mole of testosterone, meaning to get 6.022 times 10 to the 23 molecules of testosterone. Okay, that's it would take 288 grams exactly, or at least, you know, whatever value we get out there with significant figures, to get exactly a mole of testosterone. Okay, now I could go through each of these and do those with you. I do think it would be a little repetitive, and I feel like most people understand it at this point, except maybe we'll just be using different elements at this point. But remember, just use the correct subscripts, multiply them by each one. And if you did this on your own, I'll just go ahead and go through the answers here so that you're able to kind of refer to yourself, refer back to your work. And then this would be 153.18 grams per mole. This would be 176.2 grams per mole. Okay. And then lastly, 360 grams per mole. Okay. If you did all that math correctly. And that's really just the process here. You'll be doing this. You won't have to do this a ton in the class. In fact, most of the time, especially if they give you a huge molecule like this in the problem, they'll usually give you the molar mass because they're not going to test you on it specifically. But here, because we are actually learning it like this, they will test you on specific stuff like this. Okay, so I would know how to do that. Now, part C says, if you had 2 moles of each substance listed in A through D, how many moles of oxygen would each contain? Okay, so 2 moles. Okay, now let's take testosterone, for example. We're going to start with testosterone. Okay, it's saying, okay, I've got 2 moles of testosterone. Cool. Now, if for every 1 mole, let's say for every 1 molecule I have of testosterone, how many moles or atoms, I should say, of oxygen are there? There are 2, right? Atoms. Okay, so what that really means is that for every 1 mole of testosterone I have 2 moles of oxygen. Okay, and then this moles of testosterone will cancel. And they're just asking for moles of oxygen, so we're not looking for atoms of oxygen. And in this case, will be 4 moles of oxygen, okay, for testosterone. This is for in testosterone, okay? So that's how you'll kind of go about solving these. So if you go up to each one of these, you'll find that, okay, here I've got one for every 1 mole of dopamine I have. I also still have 2 moles of oxygen. So it would actually also still be 4 moles of oxygen for dopamine, because for every 1 mole of this I have, I've got 2, and I've got 2 moles of dopamine. So 2 times 2 is 4, so 4 moles of oxygen. Okay. Here on serotonin, for every 1 mole of serotonin I have 1 mole of oxygen. So that's 2 moles, because we have 2 moles of serotonin, and for every 1 mole of serotonin we have 2 moles of oxygen. So that's 2 moles of oxygen. And lastly, aldosterone, okay, for every, I have 2 moles of aldosterone and 5 moles per aldosterone. So that's a total of 10 moles of aldosterone, or of oxygen in aldosterone. So actually, the most moles of oxygen goes to aldosterone, right? Aldosterone. Okay, so that's how you'll want to solve a problem like this, all right? Okay, that will finish part 1. I know that was a little shorter than usual, but I'll be doing problems 4 through 7 in the next video.